The moon is only 3 days away. It is the one world beyond Earth that humans have actually walked on. We left footprints there more than 50 years ago, and those footprints are still sitting in the dust right now, perfectly preserved, because nothing on the moon ever changes them. No wind, no rain, no erosion. That sounds poetic until you realize what it actually means. It means there is no air, no weather, no magnetic field, no protection of any kind between your body and the raw vacuum of space. The surface swings from 260 degrees Fahrenheit in sunlight to nearly 300 below zero in shadow. The dust is made of shattered glass that charges itself and clings to everything it touches. And we want to go back and stay. If you find stories like this as fascinating as I do, a like and a subscribe genuinely help this channel keep making them. It costs nothing, and it means more than you know. Now, let's begin. Step outside tonight and look up. If the sky is clear and the timing is right, you will see the moon without a telescope, without binoculars, without any instrument at all. It is right there, a bright familiar disk hanging in the darkness, close enough that you can make out surface features with your bare eyes. Those grey patches are ancient lava plains. That bright spot near the bottom is the crater Tycho, surrounded by bright streaks of ejected material that stretch for hundreds of miles across the surface. You can see all of this from your backyard. No other world in the universe offers that kind of casual intimacy. Mars appears as a reddish dot. Jupiter is a bright point of light that reveals nothing about its nature. Saturn, Venus, Mercury, they are all abstract, tiny specks that require imagination to interpret as places. The moon is the only destination beyond Earth that actually looks like a destination. You can see its mountains, you can see its craters, you can see terrain, and something about that visibility, that simple fact that you can look up and see a world, plants a seed in the human mind that feels almost impossible to uproot. It makes the moon feel close. It makes the moon feel reachable. It makes the moon feel safe. That instinct is not wrong in every respect. The moon is close, at least by the standards of space. The average distance between Earth and the moon is roughly 238,900 miles. Light covers that gap in about 1.3 seconds. A radio signal sent from Houston to the lunar surface arrives before a human being can finish blinking. When Apollo astronauts spoke to Mission Control, the delay was so short it barely registered as a pause. Compare that to Mars, where a single message takes between 4 and 24 minutes to arrive depending on orbital positions. A conversation with Mars is impossible. You send a sentence and then wait the length of a television episode to find out if anyone heard you. Communication with the moon is practically a phone call. That difference alone rewires how the brain categorizes the two destinations. Mars feels alien and remote. The moon feels like a short trip with good cell service. The travel time reinforces this. Apollo missions reach the moon in approximately 3 days. 72 hours from launch to lunar orbit. That is shorter than a transatlantic cruise. Shorter than a cross-country road trip if you stop to sleep. A spacecraft leaving Earth on a Monday could be circling the moon by Thursday morning. Mars, by contrast, requires roughly 7 months of continuous flight through interplanetary space. 7 months sealed inside a metal container. 7 months of radiation exposure, muscle deterioration, bone loss, and psychological strain before you even arrive. And then 7 months back, the moon involves none of that. You launch, you coast, you arrive. The brevity of the trip makes it feel almost routine, like hopping on a regional flight rather than crossing an ocean. And then there is the most powerful psychological factor of all. We have already been there. Between 1969 and 1972, 12 human beings walked on the surface of the moon. They planted flags, they drove a rover, they collected rocks. They hit golf balls, they came home alive. 6 successful landings, 6 successful returns. No fatalities on the surface. The Apollo program transformed the moon from an unreachable celestial object into a confirmed human destination, a place with boot prints and tire tracks and scientific instruments sitting on the ground. That transformation lodged itself deep in the cultural memory of the entire species. The moon became familiar. The moon became known. The moon became the one place in the cosmos where humanity could say, with complete confidence, we did that. This familiarity generates a specific and very dangerous assumption. It generates the assumption that going back should be straightforward. After all, the reasoning goes, if we sent people there with 1960s technology, with less computing power than a modern smartphone, with slide rules and analog instruments, and a spacecraft held together by rivets, then surely we can do it again now, with vastly superior tools. The logic feels bulletproof. We did it once. Technology is improved by orders of magnitude. Therefore, doing it again should be easier, possibly even routine. This reasoning dominates public conversation about the moon. It shapes media coverage. It shapes political rhetoric. It shapes how ordinary people think about humanity's place in the solar system. When someone proposes returning to the moon, the reaction is rarely shock or concern. It is more likely impatience. What took so long? We should have been back decades ago. The moon occupies a mental category that no other destination in space occupies. It sits in the zone of the expected. Mars is ambitious. The asteroids are exotic. The moons of Jupiter are science fiction. But the moon is overdue. The moon is unfinished business. The moon is the destination that most people believe humanity should have already returned to by now. And at first glance, the timelines seem to support that frustration. The last Apollo mission was Apollo 17 in December of 1972, more than 53 years ago. Since then, no human being has travelled beyond low Earth orbit. The International Space Station orbits at roughly 250 miles above the surface. The moon is nearly 1,000 times farther away. For over half a century, the entire human race has been confined to a thin shell of space barely above the atmosphere, while the moon sits unvisited, its boot prints waiting. That gap between capability and action feels inexplicable to most people. It feeds the assumption that the problem was willpower, not difficulty. That we could have returned at any time if we had simply chosen to. That the moon was waiting, patient and accessible for whenever humanity decided to go back. But embedded inside that assumption is a profound misunderstanding of what the Apollo program actually was. Apollo was never designed to be sustainable. It was designed to be survivable. There is an enormous difference. The entire architecture of Apollo was built around a single objective: get human beings to the lunar surface, keep them alive for a very short time, and get them back. Every engineering decision flowed from that goal. The missions were brief. The longest surface stay was Apollo 17, during which astronauts Eugene Cernan and Harrison Schmitt spent approximately 75 hours on the moon, 3 days. And even that duration was considered an extension. Earlier missions stayed for less than 34 hours. Apollo 11, the first landing, spent just 21 hours and 36 minutes on the surface. Armstrong and Aldrin were outside the lander for barely 2.5 hours. 2.5 hours on another world, then back inside, then home. These were not expeditions. They were sprints. Carefully calculated dashes onto the surface and back before anything could go wrong. The astronauts carried their air, their water, their power, their temperature regulation, every survival requirement packed into a spacecraft and suit system designed to last days, not weeks. They did not build anything permanent. They did not repair anything that broke in a way that required long-term solutions. They encountered problems, some of them severe, but the solution to almost every problem was the same: get back in the spacecraft and leave. When lunar dust clogged equipment, the fix was to return to the lander. When the radiation exposure timer counted up, the solution was a short mission. When a fender broke off the rover on Apollo 17, sending a rooster tail of abrasive dust over everything, Cernan repaired it with duct tape and paper maps. This worked because he only needed it to last a few more hours. Nothing about this approach scales. None of it was designed to scale. Apollo proved that human beings could survive on the moon for hours. It did not prove that human beings could survive on the moon for months. It did not prove that equipment could function in the lunar environment for extended periods. It did not prove that the problems encountered, the dust, the temperature, the radiation, the vacuum, could be managed beyond the short term. What Apollo actually proved, though almost nobody frames it this way, is that a human being can stand on the moon just long enough to collect some rocks and leave before the environment kills something important. Every Apollo success came with an asterisk. The asterisk said, "This worked because we did not stay." The cultural memory erased the asterisk. What remained was the image, the flag in the grey soil, the boot print in the dust, the astronauts saluting against the black sky. Those images carry such overwhelming emotional power that they override the engineering reality underneath them. They make the moon look conquered. They make the moon look tamed. They make the moon look like a place where human beings proved they could go, which means going back should be a matter of scheduling, not survival. This is the illusion. And it is so deeply embedded that even many people within the space industry sometimes underestimate what returning to the moon actually requires. The assumption that the moon is a known quantity, a solved problem, a destination whose challenges are well understood and manageable, persists because Apollo created a false sense of completion. We went there. We came back. We know what it is like. What more is there to worry about? The answer to that question is everything. Because the moon that Apollo visited for hours is not the same challenge as the moon that any modern program intends to visit for days, weeks, or months. And the moon does not become safer the longer you stay. It becomes exponentially more dangerous. But before we reach the danger, it is important to understand just how thoroughly the moon's apparent closeness distorts human perception of it. Distance is not the only thing that makes a space destination difficult. It is not even the primary thing. What makes a destination dangerous is what happens to a human body when it arrives. And by that measure, the moon is not the gentle stepping stone that most people imagine. Consider how distance normally works in human experience. On Earth, closer means safer. If you are lost in the wilderness, being 5 miles from a road is better than being 50 miles from a road. If you are sailing in a storm, being 1 mile from shore is better than being 100 miles from shore. Proximity to safety is safety. This heuristic is so deeply encoded in human cognition that it operates below conscious thought. Closer equals better. Closer equals easier. Closer equals less risk. Space does not work this way. In space, the danger is not in the distance between you and home. The danger is in the environment at your destination. The transit is risky, certainly. Cosmic rays, equipment failure, the violence of launch and re-entry, but the destination itself is where the real hostility lies. And by that measure, the moon being 3 days away instead of 7 months away changes almost nothing about how lethal its surface is to an unprotected human being. The vacuum is the same whether you travelled 3 days or 3 years to reach it. The radiation flux is the same. The dust is the same. The temperature is the same. The moon does not become more forgiving because you can get there quickly. It simply kills you faster than a more distant destination would have made you wait. This is the conceptual trap. Proximity breeds familiarity. Familiarity breeds comfort. Comfort breeds the assumption that the destination is manageable. And the moon has been sitting in that trap for over half a century. Bathed in the afterglow of Apollo, dressed up in the mythology of 12 astronauts who touched its surface and came home, waiting for people to mistake closeness for safety. The trap is reinforced by comparison. Whenever the moon is discussed in the context of space exploration, it is almost always discussed alongside Mars, and in that pairing, the moon always comes out looking like the easier option. Mars is farther, obviously. Mars requires a longer transit. Mars has its own atmosphere, which sounds helpful until you learn it is 95% carbon dioxide, at less than 1% of Earth's atmospheric pressure. Mars has dust storms that can engulf the entire planet. Mars has a communication delay that makes real-time mission control impossible. Against all of that, the Moon looks tame. It is the local errand compared to the cross-country drive. It is the practice round before the real game. But this comparison is misleading in a critical way. It evaluates destinations by their distance and logistical complexity, rather than by the hostility of their environment to human life. And by environmental hostility, the Moon is not the gentle warm-up that the comparison implies. In certain specific ways, the Moon is actually harsher than Mars. Mars has an atmosphere. It is thin and unbreathable, but it exists. That thin atmosphere provides a small amount of radiation shielding. It creates weather patterns that, while extreme, distribute heat and interact with the surface in ways that can be studied and predicted. It slows down incoming micrometeoroids through friction, reducing surface bombardment. The Moon has none of this. The Moon has no atmosphere whatsoever. The surface sits in hard vacuum, directly exposed to every particle, every photon, every micrometeoroid that comes its way. Mars has a 24-hour day-night cycle almost identical to Earth's. The Moon's day-night cycle lasts roughly 29.5 Earth days. 14 days of relentless sunlight followed by 14 days of freezing darkness. That cycle creates thermal challenges that Mars does not impose. Mars has roughly 38% of Earth's gravity. The Moon has roughly 17%. That difference matters for human physiology in ways that are only now beginning to be studied, and the early data is not reassuring. None of this means Mars is easy. Mars is extraordinarily difficult. But the reflex to position the Moon as the simpler destination obscures the fact that the Moon's environment presents unique and severe challenges that do not automatically become manageable just because the trip is shorter. The Moon is not a stepping stone with a smooth, flat surface. It is a stepping stone covered in broken glass, sitting in a vacuum, baking and freezing on a 2-week cycle, bombarded by radiation that would be lethal to an unprotected human being within a matter of months. The Artemis program, NASA's current effort to return humans to the Moon, exists inside this perceptual framework. When Artemis was announced, the dominant public reaction was not awe or concern. It was a kind of weary expectation. It was about time. The assumption, spoken and unspoken, was that returning to the Moon was a natural next step, a logical progression, something that should have been done already and was now overdue. The program's difficulties have largely been interpreted through this lens. Delays are seen as bureaucratic failures, not as evidence of genuine technical difficulty. Cost overruns are seen as mismanagement, not as reflections of how hard the engineering actually is. The persistent framing is that we should be past this by now, that the Moon should be routine by now, that the real ambition lies elsewhere, and the Moon is merely the boring prerequisite. As of late March 2026, Artemis 2 is preparing for its first crewed flight, a flyby of the Moon without landing. Scheduled for April, this is the first time humans will travel beyond low Earth orbit since 1972. The mission has been delayed multiple times. Originally targeted for late 2024, it slipped to 2025, then to early 2026, then through several windows within 2026. A hydrogen leak discovered during a fueling test in February pushed the timeline again. The first human landing, originally planned as Artemis 3, has been restructured. In a February 2026 press conference, NASA announced that Artemis 3 would no longer include a surface landing. That milestone has been moved to Artemis 4. The first human boots on the Moon since Apollo will not happen until 2027 at the earliest, and many analysts expect further delays. These setbacks are not failures of will. They are failures of expectation. The expectation was that returning to the Moon would be a relatively straightforward engineering challenge because we had done it before. The reality is that the engineering is staggeringly complex, not because the technology is insufficient, but because the ambitions are fundamentally different from Apollo, Artemis does not intend to sprint to the surface and sprint home. It intends to build a sustainable presence. It intends to send astronauts to the lunar South Pole, a region never visited by Apollo where permanently shadowed craters may contain water ice. It intends to build a small orbital station called Gateway. It intends to develop surface habitats, power systems, and resource extraction technologies. Every one of these goals requires solving problems that Apollo never attempted, in an environment that Apollo barely survived for hours. The mismatch between public expectation and engineering reality is the direct product of the comfortable illusion. People expect returning to the moon to be manageable because the moon feels manageable. It is close. It is familiar. It is the one alien world that looks like a world when you glance at the night sky. And every delay, every setback, every restructured mission is interpreted as evidence that something has gone wrong with the program, rather than evidence that the destination itself is more hostile than anyone wants to admit. There is a phrase that appears constantly in discussions about Lunar: exploration, going back. We are going back to the moon. The language itself reveals the assumption. Going back implies returning to a known place, revisiting a familiar location, retracing a path already walked. It carries the emotional weight of homecoming. You go back to a city you once lived in. You go back to a restaurant you enjoyed. Going back is comfortable, it is expected, it is safe. But humanity is not going back to the moon in any meaningful sense. The moon that Artemis intends to visit is not the moon that Apollo visited. Apollo visited the equatorial regions during lunar daytime for hours, with no intention of staying. Artemis intends to visit the South Pole, where lighting conditions are extreme, where temperatures in permanently shadowed craters plunge far below anything ever recorded on Earth's surface, and where the terrain has never been directly observed at human scale. The engineering challenges of the South Pole are categorically different from the challenges Apollo faced. The thermal environment is more extreme. The terrain is more hazardous. The lighting is more difficult, with the sun sitting perpetually near the horizon, casting long shadows that make navigation treacherous and creating temperature gradients of hundreds of degrees across distances of meters where sunlight and shadow meet. Going back to the moon is not going back to anything. It is going forward into a challenge that exceeds Apollo in almost every dimension. Apollo proved that humans could touch the moon. It did not prove that humans could live there. And the difference between touching and living is not a matter of degree. It is a matter of kind. Yet, the illusion persists. The moon hangs in the sky tonight, bright and familiar, looking exactly the way it has looked for every generation of human beings that has ever lived. It looks peaceful. It looks patient. It looks like it is waiting for us to come back. It looks like the easy destination, the natural next step, the one place in the cosmos where humanity already knows what to expect. That expectation is about to collide with a physical reality so harsh that it redefines what the word hostile means in the context of space exploration. Because everything that makes the moon look familiar from 239,000 miles away vanishes the moment you stand on its surface. And what replaces it is a world that attacks human survival in ways that most people have never been asked to imagine. What the moon actually does to the human body, to human equipment, and to every assumption about safety that human beings carry unconsciously from their lives on Earth begins with a simple, brutal question. What exactly does the Earth do for you that you have never once had to think about? You have never taken a breath that the planet did not prepare for you. Right now, as your eyes move across these words, your lungs are pulling in air that was filtered, pressurized, temperature regulated, and chemically balanced by a system so vast and so reliable that you have never once had to think about it. The atmosphere above your head stretches roughly 60 miles upward. It weighs approximately 5.5 quadrillion tons. It presses against every square inch of your body at 14.7 pounds per square inch. And it has been doing so since the moment you were born with such perfect consistency that your nervous system does not even register it as a sensation. You cannot feel the atmosphere. You cannot see it. You walk through it like it is nothing. But it is not nothing. It is the single most important survival system that any human being has ever depended on. And it does at least half a dozen things simultaneously that keep you from dying in the next 30 seconds. It gives you oxygen. Not just oxygen floating loosely in space, but oxygen mixed at precisely the right concentration, roughly 21% of the total atmospheric volume, blended with nitrogen and trace gases in a ratio that your blood chemistry requires. Too much oxygen and your tissues oxidize. Too little and your cells starve. The atmosphere maintains this balance globally, continuously, without interruption, across the entire surface of the planet. Every breath you have ever taken was drawn from this reservoir. Every breath every human being has ever taken was drawn from this reservoir. And on the moon, this reservoir does not exist. There is no air. Not thin air. Not bad air. No air. The lunar surface sits in a vacuum so complete that it qualifies as a better vacuum than most laboratory equipment on Earth can produce. The few molecules that drift above the surface, a scattering of helium, neon, hydrogen, and argon, are so sparse that scientists classify them as an exosphere rather than an atmosphere. Their combined density is roughly 100 trillion times less than the air in your living room. For all practical purposes, the moon has nothing between its surface and the void of deep space. The implications of this are immediate and lethal. A human being exposed to hard vacuum without a pressure suit loses consciousness in approximately 10 to 15 seconds as the oxygen in the blood is consumed without replacement. What follows is not a gentle loss of consciousness. It is a rapid, violent physiological breakdown that proceeds on a timeline measured in seconds, not minutes. Death follows within 1 to 2 minutes if the exposure is not reversed. This is not a theoretical scenario. It is established aerospace medicine, but the clinical summary understates the violence of the process. Decompression in hard vacuum is not a quiet fading. It is a systematic assault on every pressurized system in the body. The first thing to fail is the respiratory system. The lungs, designed to operate at sea level pressure, cannot transfer oxygen into the bloodstream when the external pressure drops to zero. The partial pressure of oxygen in the alveoli falls below the threshold needed to drive diffusion into the blood. Within seconds, the oxygen already dissolved in the blood is consumed by metabolizing tissues and not replaced. The brain, which accounts for roughly 20% of the body's oxygen consumption, despite representing only 2% of its mass, is the first organ to notice. Consciousness narrows. Decision-making collapses. The ability to take corrective action, to reach for an emergency SEAL kit, to activate a backup system, to even understand that something has gone wrong, disappears within 10 to 15 seconds. This is not enough time to troubleshoot. It is barely enough time to recognize the problem. Simultaneously, the reduction in external pressure causes dissolved gases in the body's fluids to come out of solution. Nitrogen, which makes up roughly 78% of the air you breathe and dissolves into your blood and tissues at sea level pressure, forms bubbles as the surrounding pressure drops. These bubbles can lodge in joints, causing excruciating pain. They can block capillaries in the brain, causing stroke-like symptoms. They can form in the tissues around the spinal cord, causing paralysis. This is the same mechanism that kills deep-sea divers who ascend too quickly. Except in vacuum, the pressure drop is not from 2 atmospheres to 1. It is from 1 atmosphere to 0. The entire dissolved gas load in the body attempts to escape at once. The water in exposed mucous membranes, the moisture on the eyes, the saliva on the tongue, begins to boil at body temperature, because the boiling point of water is a function of pressure, and at near zero pressure that boiling point drops below 37 degrees Celsius. This is not thermal boiling. The tissues are not hot. They are simply exposed to a pressure regime in which liquid water at body temperature transitions to vapor. The swelling of soft tissues follows as water vapor expands beneath the skin. Animal studies conducted during the early space program documented the progression in seconds, not minutes. The body does not gently shut down in vacuum. It comes apart. Every second a human being spends on the lunar surface, they are separated from this outcome by nothing more than the integrity of their suit or habitat. One puncture, one seal failure, one micrometeoroid strike in the wrong place. The margin between life and the vacuum is measured in millimeters of fabric and metal. But the atmosphere does far more than provide air to breathe. It is also a radiation shield of extraordinary effectiveness, and you have never had to think about that either. Right now, as you sit hearing this, your body is being bombarded by cosmic radiation. High-energy particles originating from supernova explosions, distant galaxies, and the sun itself are streaming through space in every direction. Some of these particles travel at nearly the speed of light. They carry enough energy to shatter DNA molecules, break chemical bonds inside living cells, and initiate cascading damage that can lead to cancer, neurological deterioration, and organ failure. These particles are everywhere in space. They are constant, and they are hitting the top of Earth's atmosphere right now, in enormous quantities every second of every day. You do not notice because the atmosphere stops them. When a high-energy cosmic ray strikes the upper atmosphere, it collides with nitrogen and oxygen molecules, generating a shower of secondary particles that lose energy as they cascade downward. By the time any remnant reaches the surface, its energy has been dissipated across billions of molecular interactions. The atmosphere acts as a shield equivalent to roughly 1,000 grams of material per square centimetre, or about the same protection as a wall of water 10 meters thick. This is not a metaphor. This is the literal shielding value of the air above your head. You are walking around at the bottom of an ocean of gas that absorbs lethal radiation before it reaches you. The annual radiation dose at sea level on Earth from cosmic sources is approximately 0.3 millisieverts. It is so low that it ranks below the dose you receive from the natural radioactivity of the soil and rocks beneath your feet. The Moon has no such shield. Cosmic rays reach the lunar surface at full energy. Galactic cosmic radiation on the Moon delivers an annual dose of approximately 380 millisieverts during solar minimum conditions, when the Sun's magnetic field is weakest and provides the least deflection. During solar maximum, the dose drops to roughly 110 millisieverts because the Sun's heightened magnetic activity deflects some galactic particles. But solar maximum brings its own danger. Solar particle events, sudden eruptions of protons and heavier ions from the Sun's surface, can deliver acutely dangerous radiation doses within hours. A major solar particle event can expose an unshielded astronaut on the lunar surface to more than 1 sievert in a single episode. For context, 1 sievert delivered rapidly is enough to cause acute radiation syndrome, nausea, vomiting, and measurable damage to blood-forming tissues. Doses above 3 to 4 sieverts become increasingly fatal without medical intervention. And on the Moon, there is no medical intervention that matches what an intensive care unit on Earth could provide. There is no shielded treatment facility. There is a suit or a habitat and whatever shielding mass those structures happen to carry. The numbers require careful framing because radiation risk is cumulative and probabilistic rather than instantly lethal in most scenarios. An astronaut spending a year on the lunar surface would accumulate a radiation dose roughly 150 to 200 times higher than a person living at sea level on Earth for the same period. Career dose limits for astronauts set by space agencies attempt to keep lifetime cancer risk increases below acceptable thresholds, but those limits were designed for missions in low Earth orbit, where the International Space Station benefits from partial shielding by Earth's magnetic field. The lunar surface has no magnetic protection at all. Earth's magnetic field, generated by convection currents in the planet's molten iron core, extends tens of thousands of miles into space, creating a protective bubble called the magnetosphere. Charged particles from the solar wind are deflected around this bubble, channeled toward the poles where they produce the aurora. The magnetosphere is invisible, intangible, and absolutely critical. Without it, the solar wind would gradually strip the atmosphere away, as it did on Mars billions of years ago when Mars lost its global magnetic field. The Moon never had a significant long-duration global magnetic field in the way Earth does. It has localized magnetic anomalies, small patches of remnant magnetism in the crust, but nothing that provides meaningful protection across the surface. The Moon sits fully exposed to both the solar wind and galactic cosmic rays, unshielded from above and unshielded from the sides. This matters in ways that go beyond the primary radiation dose. When high-energy particles strike the lunar surface, they do not simply stop. They interact with the regolith, the rocky soil, and produce secondary radiation. Neutrons, gamma rays, and additional charged particles scatter upward from the ground, creating an albedo radiation field that hits an astronaut from below. This means a person standing on the Moon is irradiated from two directions simultaneously: cosmic rays from above and secondary particles from the ground beneath their feet. No suit design can fully address this because the radiation comes from the entire surrounding environment. This albedo radiation field is one of the least discussed and most insidious aspects of the lunar radiation environment, because it violates the intuitive assumption that shielding works by putting mass between you and the source. On Earth, if radiation comes from above, you go inside a building. The roof and walls absorb the incoming particles, problem solved. On the Moon, the primary cosmic rays come from above, but the secondary radiation generated by their interaction with the regolith comes from below and from every surrounding surface. An astronaut standing on the lunar plane is effectively standing inside a radiation bath. Shielding the top and sides of a habitat does not address the neutrons and gamma rays streaming upward through the floor. Addressing the floor requires mass beneath the habitat as well, which either means burying the structure or elevating it on a platform with shielding material underneath. Neither solution is trivial. Both require construction capability on the surface that does not yet exist. The radiation environment on the Moon is not a beam that can be blocked with a wall. It is a field that surrounds you, and the ground you walk on is one of its sources. In January 2026, NASA selected the Selene instrument payload from Johns Hopkins Applied Physics Laboratory specifically to characterize this combined primary and secondary radiation environment on the lunar surface for the first time with comprehensive measurements. The fact that this characterization has not yet been completed tells you something important. More than 50 years after Apollo, we still do not have a full, detailed picture of the radiation hazard on the Moon. We have models, we have calculations, we have brief measurements from Apollo-era dosimeters, but the complete ground truth remains uncollected. Set radiation aside for a moment and consider something even more immediately intuitive. Temperature. You live inside a thermal envelope so precisely regulated that your body barely has to work to maintain its core temperature. Earth's atmosphere traps heat through the greenhouse effect, distributes it through wind and ocean currents, and releases it gradually through radiation to space. The result is a planetary surface where temperatures in inhabited regions generally range between -40 and 50 degrees Celsius, a band of roughly 90 degrees within which human life, agriculture, and civilization can function. Most people live in an even narrower range. The difference between a hot summer day and a cold winter night in a temperate city might be 40 degrees. Your body handles this range with modest effort, sweating to cool down, shivering to warm up, seeking shade or shelter as needed. The Moon operates on a completely different thermal regime. At the lunar equator, surface temperatures during the day reach approximately 127 degrees Celsius. That is above the boiling point of water and hotter than the maximum temperature of most industrial ovens used for drying or curing. At night, the same surface drops to approximately -173 degrees Celsius. That is colder than any naturally occurring temperature ever recorded on Earth's surface. Colder than the coldest point in Antarctica. Colder than liquid nitrogen. The total swing between lunar noon and lunar midnight is roughly 300 degrees Celsius. 300 degrees of thermal variation on a single world, at a single location, during a single day-night cycle. But here is what makes this truly punishing. The lunar day-night cycle is not 24 hours. It is roughly 29.5 Earth days. That means the surface bakes in direct sunlight for approximately 14 consecutive Earth days, then freezes in darkness for another 14. There is no rapid cycling. There is no dawn relief after a few hours of cold. When the sun sets on the moon, it does not rise again for 2 weeks. 14 days of unbroken darkness, during which the surface radiates its heat directly into space with nothing to slow the process. No atmosphere to retain warmth, no ocean to buffer the transition, no clouds to reflect heat back downward. The surface simply cools relentlessly for 336 hours straight. And then when the sun returns, it beats down on the surface for another 336 hours straight, heating the regolith without any atmospheric diffusion to moderate the intensity. The permanently shadowed regions near the lunar poles present an even more extreme case. Because the moon's axis is tilted only about 1.5 degrees relative to the plane of its orbit, certain deep craters near the poles have floors that never receive direct sunlight, ever. Not during any part of the lunar day, not during any season, not during any year. These permanently shadowed regions have been measured by NASA's Lunar Reconnaissance Orbiter Diviner instrument at temperatures as low as -238 degrees Celsius. That is 35 degrees above absolute zero, colder than the surface of Pluto, among the coldest temperatures measured anywhere in the solar system. And these are precisely the regions where Artemis missions intend to send astronauts, because the extreme cold may have preserved water ice that could be valuable for future operations. The thermal challenge is not merely academic. It affects every piece of equipment, every structural material, every mechanical joint, every seal, every wire, and every electronic component brought to the surface. Materials expand when heated and contract when cooled. A 300-degree thermal swing imposes enormous mechanical stress on any structure exposed to the full cycle. Metals fatigue. Seals crack. Lubricants that work at room temperature either evaporate in the heat or freeze solid in the cold. Electronics designed for terrestrial temperature ranges fail. Batteries lose capacity in extreme cold and degrade in extreme heat. Solar panels that generate power during the 14-day day become useless during the 14-day night, requiring either nuclear power sources or massive energy storage systems to keep habitats alive through the darkness. Every Apollo mission was carefully scheduled to operate during lunar morning, when temperatures were rising but had not yet reached their peak, and every mission departed long before nightfall. No Apollo crew ever experienced the lunar night. No human being ever has. Now add one more layer of protection that Earth provides and the Moon does not. Pressure. The atmospheric pressure at sea level is a consequence of the weight of the air above you, and your body is adapted to it at the deepest level. Your lungs inflate against this pressure. Your blood vessels maintain their integrity because internal fluid pressure and external atmospheric pressure are in equilibrium. Your sinuses, your inner ears, your eyes, every gas-filled cavity in your body exists in a state of balance with the surrounding atmosphere. Remove that external pressure, and the catastrophic sequence described earlier begins. The body becomes, in a very real sense, a pressurized container in an environment that no longer supports its internal state. You already know what happens next. The point here is not the physiology of decompression but the engineering consequence. Maintaining pressure is not one requirement among many. It is the prerequisite for all the others. Without it, oxygen delivery is irrelevant, thermal regulation is irrelevant, radiation shielding is irrelevant. You are dead in 2 minutes. Pressure integrity is the foundation on which every other survival system rests. And on the Moon, that foundation is only as strong as the thinnest wall between you and the vacuum. On the Moon, the only thing maintaining that pressure is the suit or the habitat wall. This is not like wearing a coat against the cold. A pressure garment must maintain a complete, sealed, gas-tight enclosure around the entire body while simultaneously allowing the person inside to move, work, bend, grip tools, walk over rough terrain, and perform tasks that require fine motor control. The internal pressure of a spacesuit is significantly lower than sea level atmospheric pressure, typically around 4.3 pounds per square inch for NASA's current suit designs, compared to 14.7 at sea level. This lower pressure is necessary to keep the suit flexible enough to move in, but it requires the astronaut to pre-breathe pure oxygen to purge nitrogen from their blood and avoid decompression sickness. Even at this reduced pressure, the suit is stiff. Every finger flex, every arm raise, every step requires working against the rigidity of a pressurized garment. Apollo astronauts reported extreme fatigue in their hands and forearms after surface excursions, with some developing blisters and losing fingernails from the effort of gripping tools inside pressurized gloves. And all of this, every system, every layer of protection, every engineering solution, must function simultaneously and without interruption for the entire duration of the mission. On Earth, these survival functions operate independently and redundantly. If the temperature drops, you find shelter. If the air quality declines, you move to a different location. If radiation increases, you go indoors. Each threat has a separate, independent solution, and the failure of one does not affect the others. On the Moon, everything is coupled. The same suit that provides pressure also provides oxygen, temperature regulation, radiation shielding, and communication. A failure in any one system potentially compromises all of them. The same habitat that provides atmosphere also provides thermal control, power, water recycling, and waste management. There is no backup environment. There is no second option. If the habitat fails, the suit is the only alternative. If the suit fails, there is nothing. This total dependence on engineered systems is what makes the Moon fundamentally different from any environment humans have ever inhabited on Earth, including the most extreme ones. People live in the Arctic. People live in deserts. People live at high altitudes. In every one of these environments, the natural world still provides a baseline of survival support. There is always air. There is always some atmospheric pressure. There is always some protection from cosmic radiation. The challenge in extreme terrestrial environments is supplementing what nature provides. On the Moon, nature provides nothing. The challenge is replacing everything, from scratch, using systems that cannot fail, in an environment that actively degrades those systems every moment they operate. Consider gravity itself. This is the one environmental factor that most people never think about as a survival requirement, because on Earth, it is simply a given. Gravity holds the atmosphere in place. It keeps water in liquid form on the surface. It maintains the pressure gradient that allows your cardiovascular system to function, and it loads your skeleton and muscles in ways that are essential for their continued health. The Moon's gravity is approximately 1/6 of Earth's. This means a person who weighs 180 pounds on Earth weighs about 30 pounds on the Moon. At first consideration, this sounds pleasant, even fun. Bounding across the surface in long, slow arcs, lifting heavy equipment with ease, the Apollo astronauts certainly appeared to enjoy it. But the reduced gravitational load has consequences for the human body that only become apparent over time, and the time frame required for serious damage is shorter than most people assume. On the International Space Station, where astronauts experience near-zero gravity, bone density decreases at a rate of approximately 1 to 2% per month, despite rigorous daily exercise. Muscle mass can decline by 10 to 20% within several weeks. Cardiovascular deconditioning occurs as the heart, no longer working against gravity to pump blood upward, begins to weaken and shrink. Fluid shifts toward the head, increasing intracranial pressure and causing vision problems that have been documented in a significant percentage of long-duration station crew members. These effects occur in microgravity, at effectively zero gravitational load. The question for lunar operations is whether 1/6 gravity is enough to prevent or significantly slow these changes. The answer, based on the best evidence available, is not encouraging. A 2024 study, published in Scientific Reports, examined mice housed on the International Space Station under 3 conditions. microgravity, artificial lunar gravity at 1/6 of Earth's value, and full Earth gravity. The results showed that bone density reduction under microgravity was only partially recovered under lunar gravity. Thymus atrophy, an indicator of immune system degradation, was only half recovered. Gene expression changes associated with bone resorption and immune function were not fully suppressed at 1/6 gravity. A separate study published in Communications Biology found that while lunar gravity prevented gross muscle atrophy in the soleus muscle of mice, it did not prevent the shift in muscle fiber type composition that occurs under reduced loading, a change associated with reduced endurance and altered muscle function. A NASA technical paper reviewing multiple studies concluded that partial gravity exposure below approximately 0.4 times Earth's gravity, a threshold well above the Moon's 1/6 value, appears insufficient to maintain musculoskeletal and cardiopulmonary conditioning over the long term. This means that astronauts living and working on the Moon for extended periods would likely experience ongoing bone loss, muscle weakening, cardiovascular changes, and immune suppression, even though they are standing on a solid surface and walking around under gravity. The gravity is simply not enough. 1/6 of a force that your body requires in full is not a partial solution. It is a partial version of the problem. And the longer the stay, the more the deficits accumulate, and the harder the eventual return to Earth's full gravity becomes. Earth does all of this for you, every moment of every day. It wraps you in air. It shields you from radiation. It presses against your body with exactly the right force to keep your fluids liquid, your lungs functional, and your blood flowing. It holds you down with exactly the right gravitational pull to maintain your bones, your muscles, your heart, and your balance. It moderates temperature across a range your body can manage. It filters out the lethal wavelengths of solar radiation while letting through the visible light you need to see and the warmth you need to survive. It does all of this automatically, redundantly, and without any input from you whatsoever. You have never had to think about any of it. You have never had to maintain any of it. You have never had to build a machine to replace any of it. The Moon requires you to replace all of it, every function, every protection, every parameter, simultaneously, continuously, with no margin for error and no fallback if the systems that replace Earth's protections fail. And here is the part that most discussions of lunar exploration skip entirely. Even if you solve every one of these problems, even if you build a perfectly sealed, perfectly pressurized, perfectly shielded, perfectly temperature-controlled habitat, and you keep it running flawlessly for months, you still have to go outside. You have to conduct surface operations. You have to walk on the regolith, handle equipment, collect samples, maintain hardware, build infrastructure. Every time you step outside the habitat, you trade the controlled environment for the raw lunar surface. Every excursion is an exposure event. Radiation accumulating, dust contaminating suit systems, thermal stress cycling through your equipment, the vacuum pressing against your only barrier with absolute patience, waiting for the smallest failure. And that is before you account for the thing that makes the Moon uniquely, specifically, aggressively dangerous in a way that no amount of distance from Earth can explain and no amount of engineering has yet solved. The surface itself is not merely barren, it is hostile. It is made of a material that attacks every system it contacts, biological and mechanical alike, and it has been refined by 4.5 billion years of bombardment into the most insidious environmental hazard in the inner solar system. That material deserves its own reckoning, and it is the reason Apollo astronauts, after just hours on the surface, warned that lunar dust might be the single greatest obstacle to long-term operations on the Moon. 50 years later, they have not been proven wrong. Everything up to this point has been about absence. No air, no pressure, no magnetic field, no radiation shielding, no thermal regulation. The Moon fails to provide the protections that Earth supplies automatically, and that failure alone is enough to make it lethal. But the Moon's hostility does not stop at what it lacks. The lunar surface is covered in a material that does not merely sit beneath your feet. It infiltrates, abrades, corrodes, and contaminates every object and every organism it touches. It is not passive terrain. It is an active threat, and it has been waiting on the moon for 4.5 billion years, growing more dangerous with every passing century, sharpened by a process that has no equivalent anywhere on Earth. Lunar regolith is the layer of broken rock, mineral fragments, and fine dust that blankets the entire surface of the moon to a depth of several meters in most locations and up to 15 meters in the older highland regions. It was not deposited by wind or water. It was created by violence. For billions of years, the moon has been struck by meteoroids of every size, from boulders the size of buildings to particles smaller than grains of sand. Each impact shatters surface rock, pulverizes existing fragments, and generates a fresh layer of broken material that settles back onto the surface. Over geological time, this relentless bombardment has ground the upper crust into a blanket of debris that covers everything. There is no bedrock exposure on the moon that has not been processed by impacts. Every square meter of the surface is coated in the shattered remnants of collisions stretching back to the formation of the solar system. On Earth, broken rock gets softened. Wind rolls sand grains against one another, rounding their edges. Water dissolves sharp mineral faces. Chemical weathering breaks down reactive surfaces. Freeze-thaw cycles fracture material along planes that produce relatively smooth fragments. The result is that terrestrial dust and sand, while sometimes irritating, consists of particles that have been mechanically and chemically processed into comparatively gentle forms. Beach sand is smooth. Desert dust is fine but rounded. Soil particles have been worked and reworked by biological and chemical processes for millions of years. They are, in geological terms, tamed. Lunar regolith has never been tamed. There is no wind on the moon to round the edges. There is no water to dissolve the sharp faces. There is no chemical weathering, no biological processing, no erosion of any kind. When a micrometeorite strikes the surface and shatters a mineral grain, the resulting fragments retain every jagged edge, every razor-sharp fracture surface, every needle-like protrusion that the physics of fracturing created. Those fragments sit on the surface exactly as they were made, century after century, millennium after millennium, with nothing to dull them. The particles are angular, irregular, and extraordinarily abrasive. Electron microscope images of lunar regolith samples, brought back by Apollo, reveal shapes that look like shattered glass, because in many cases that is precisely what they are. Impact events generate enough heat to melt rock and silicate minerals, which then cool into tiny glass beads and glass-coated fragments called agglutinates. These glassy particles are among the sharpest and most abrasive components of the regolith. They are not rounded spheres. They are jagged, irregular shards with hooks, barbs, and edges that catch and cling to any surface they contact. The particle size distribution makes this worse. Lunar regolith contains grains across a wide spectrum, from coarse fragments several millimeters across down to ultrafine particles measured in fractions of a micron. The finest fraction, particles smaller than 20 microns, is classified as lunar dust, and this is where the real danger lives. Particles below 10 microns are small enough to penetrate deep into human airways. Particles below 2.5 microns can reach the alveoli, the tiny air sacs in the lungs where oxygen exchange occurs. Lunar dust contains significant quantities of particles in both of these size ranges. Some particles are as fine as a few hundredths of a micron, small enough to pass through biological membranes and interact directly with individual cells. On Earth, comparable particles from industrial sources are associated with silicosis, pulmonary fibrosis, and elevated cancer risk. Lunar dust shares many physical characteristics with the mineral particles that cause these diseases, and in some respects may be worse, because the particles have never been exposed to moisture or oxygen that might passivate their most reactive surfaces. Here is where the moon does something that Earth dust cannot. Lunar dust charges itself. The surface of the Moon is continuously exposed to two sources of electrical charging. The first is the solar wind, a stream of charged particles, primarily protons and electrons, flowing outward from the Sun at speeds of roughly 400 kilometers per second. When these particles strike the lunar surface, they interact with regolith grains, depositing charge and altering the electrical potential of the surface layer. The second source is solar ultraviolet radiation, which is energetic enough to knock electrons off the surfaces of mineral grains through the photoelectric effect. During the lunar day, sunlit surfaces become positively charged as electrons are ejected, while shadowed regions accumulate negative charge from solar wind electrons that are not offset by photoelectric emission. This creates a complex, dynamic electrical environment where the surface charge varies dramatically across short distances, particularly near the boundary between sunlit and shadowed terrain. The charging has a direct physical consequence. Charged dust grains are attracted to surfaces through electrostatic forces. They do not merely land on objects and sit passively, they actively cling. They adhere to suit fabric, to visor glass, to metal surfaces, to seals, to joints, to every exposed component with a tenacity that mechanical brushing cannot fully overcome. Apollo astronauts discovered this within minutes of their first surface excursions. Dust coated everything. It climbed up their suits from the boots. It covered their visors. It embedded itself in the woven fibers of the suit material so thoroughly that no amount of brushing could remove it. When the astronauts returned to the lunar module and repressurized the cabin, the dust came with them. It floated in the air. It coated the instrument panels. It got into their eyes. It got into their lungs. Harrison Schmitt, the geologist astronaut on Apollo 17, reported symptoms he described as lunar hay fever almost immediately after removing his helmet inside the lunar module. Nasal congestion, sneezing, and irritation that lasted for hours. Other Apollo crew members reported similar respiratory effects, though the exposures were brief, limited to the few hours of cabin contamination between surface excursions and the return to orbit. Medical evaluations after the missions found evidence of airway irritation, and one analysis of Apollo 17 crew data suggested measurable reductions in lung function on the order of 10 to 20% following dust exposure. These were young, exceptionally fit military test pilots and scientists experiencing respiratory effects after just a few hours of indirect exposure to lunar dust inside a pressurized cabin. The toxicity mechanisms are not yet fully understood, and this itself is part of the problem. The complete biological effects of prolonged lunar dust inhalation have never been studied in humans because no human has ever been exposed for more than a few days, and even those exposures were incidental rather than deliberate. What exists is a body of laboratory research using lunar dust simulants and the limited supply of actual Apollo regolith samples that were returned to Earth. These studies paint a concerning picture. Lunar dust particles are mechanically irritating due to their sharp, angular shapes. They can penetrate deep into lung tissue and cause inflammation through physical damage to cell membranes. But there is also evidence of chemical reactivity. Fresh lunar dust, meaning dust whose surfaces have not been passivated by exposure to oxygen and moisture, may generate reactive oxygen species when it contacts biological tissue. These free radicals can damage DNA, trigger inflammatory cascades, and contribute to cell death. A 2022 review published in NPJ Microgravity catalogued the known and hypothesized risks, including pulmonary fibrosis, chronic airway inflammation, corneal abrasion, and potential synergistic effects with radiation exposure. The authors noted that the full spectrum of health effects from chronic low-dose exposure remains unknown, and identified this as a critical gap in planning for extended lunar missions. Whether the dust on the actual lunar surface is more or less reactive than simulants remains an open question. Some evidence suggests that the surface reactivity of regolith grains is rapidly neutralized upon exposure to air and moisture inside a spacecraft. Other studies indicate that the reactive state may persist for hours after initial atmospheric contact. The true hazard may depend on how quickly dust enters the habitat environment after being brought in on suits and equipment, how effectively filtration systems can capture ultrafine particles, and whether repeated exposure cycles create cumulative damage that single exposure studies cannot predict. No one has the definitive answers because the experiment has never been conducted at the necessary duration and scale. NASA clearly considers this a serious and unresolved risk. In late 2025, the agency awarded $24.8 million to the University of Colorado Boulder's Laboratory for Atmospheric and Space Physics to build the Duster instrument payload, specifically designed to study charged lunar dust and near-surface plasma at the Moon's south pole during the Artemis 4 mission. The instrument suite will measure dust particle charge, speed, size, and flux, along with electron density profiles above the surface. The principal investigator stated publicly that developing a complete picture of the dust and plasma environment is essential for ensuring astronaut safety and the operation of exploration equipment. The fact that this instrument has not yet been deployed, that the comprehensive ground truth characterization of the dust environment at the planned Artemis landing sites remains incomplete more than 50 years after Apollo, tells you something about the scale of what remains unknown. But the biological threat is only part of the story. Lunar dust is equally destructive to hardware, and in some ways the engineering consequences are even more immediate than the health consequences. During Apollo missions, dust contamination degraded equipment performance within hours. Thermal control surfaces, the radiators that spacecraft and suits use to reject excess heat into space, rely on specific optical properties. They must absorb minimal solar energy and emit thermal infrared radiation efficiently. When dust coats these surfaces, it changes their optical characteristics. Solar absorptance increases, meaning the surface absorbs more heat from sunlight. Emittance decreases, meaning the surface becomes less efficient at radiating heat away. The net result is overheating. Apollo data showed that dust contamination reduced the efficiency of thermal radiators by up to 50%. On missions lasting days, this was manageable. On missions lasting months, it could be fatal to equipment and dangerous to crews relying on thermal regulation systems. Seals and mechanical joints suffered similar degradation. The fine, abrasive particles worked their way into every gap, every interface, every moving part. They acted like grinding paste, accelerating wear on bearing surfaces and compromising the integrity of seals designed to maintain pressure boundaries. The Apollo Lunar Surface Journal contains detailed accounts of dust clogging equipment, jamming mechanisms, and fouling optical instruments. Camera lenses became scratched and hazy. Suit joints stiffened as dust accumulated in the bearings. Equipment designed and tested in clean terrestrial environments discovered a new failure mode within hours of exposure to the regolith. The Apollo lunar laser retroreflectors provide a haunting long-term example. These devices, essentially arrays of precisely aligned corner cube reflectors, were placed on the surface during Apollo 11, 14, and 15 to allow laser ranging experiments from Earth. They require no power, they have no moving parts, they simply reflect laser light back toward Earth. They have been in continuous use for over 50 years, but the signal strength returned by these reflectors has decreased by a factor of 10 to 100 since their deployment. The primary suspected cause is dust accumulation on the reflector surfaces, gradually reducing their optical performance. These are the simplest possible instruments, passive glass surfaces with no mechanisms to fail, and the dust has degraded them by orders of magnitude across 5 decades of exposure. Imagine what that process does to active instruments, to solar panels, to windows, to any optical or thermal surface that a long-duration mission depends on. Now consider the environment that creates and mobilizes this dust in ways that have no terrestrial parallel. The Moon has no atmosphere to slow. Incoming objects, micrometeoroids, tiny particles of cometary and asteroidal debris ranging from specks smaller than a grain of salt to fragments the size of a pebble, strike the lunar surface at velocities typically between 10 and 72 kilometers per second. On Earth, The atmosphere decelerates and vaporizes, all but the largest incoming particles. The shooting stars you see on a clear night are millimeter-sized grains burning up at altitudes of 80 to 100 kilometers, destroyed long before they reach the ground. On the Moon, those same particles reach the surface at full velocity. A particle weighing a fraction of a gram, traveling at 20 kilometers per second, carries kinetic energy equivalent to a small caliber bullet. It strikes the regolith, excavates a crater many times its own diameter, and generates a spray of secondary ejecta, tiny high-velocity fragments launched outward from the impact site. This process is continuous. The flux of micrometeoroids at the Moon's distance from the Sun is constant. Every square meter of the lunar surface receives impacts at a statistically predictable rate, and the cumulative effect over time is significant. It is not a rainstorm. It is more like standing in a field where a tiny bullet strikes somewhere within a few kilometers of you every few seconds. The probability of a direct hit on any specific piece of equipment in any given hour is very small, but the probability of a hit somewhere on a large installation over the course of months or years is not negligible. And because there is no atmosphere to provide warning or deceleration, there is no defense other than physical shielding. You cannot detect a millimeter-sized particle traveling at 20 kilometers per second until it has already hit something. The ejecta from these impacts also contribute to dust mobilization. Each micrometeorite strike launches a shower of regolith particles on ballistic trajectories. Some of these particles travel considerable distances before settling back onto the surface. This creates a constant, low-level rain of secondary dust particles across the lunar landscape, a process that has been going on for billions of years and will continue indefinitely. Any equipment left on the surface accumulates this secondary deposit on top of whatever electrostatic dust adhesion is already occurring. The two processes compound each other. Electrostatic forces hold dust in place once it arrives. Impact ejecta continuously deliver fresh material. The surface of any object on the Moon gets dirtier over time, not cleaner, and there is no natural process that reverses the accumulation. Rocket exhaust during landing and takeoff presents an additional and severe dust mobilization hazard. When a descent engine fires near the lunar surface, the exhaust gases interact directly with the regolith. There is no atmosphere to contain the blast or slow the ejected particles. Studies of Apollo landing sites and analysis of the Chinese Chang'e missions have shown that engine exhaust can accelerate regolith particles to velocities of hundreds or even thousands of meters per second, launching them on trajectories that carry them kilometers from the landing site. These high-velocity particles can sandblast any equipment, habitats, or instruments in the surrounding area. If future missions establish permanent infrastructure near a landing zone, every subsequent landing becomes a potential damage event for everything already on the surface. This problem has no obvious solution short of establishing dedicated landing pads made from processed regolith, which itself requires extensive surface operations to construct before regular traffic can begin. The combined effect of all these dust-related hazards creates a degradation curve for equipment and systems that is fundamentally unlike anything encountered in terrestrial engineering. On Earth, equipment degrades primarily through oxidation, moisture intrusion, biological fouling, and mechanical wear under normal use. These processes are well understood, and maintenance schedules can be designed around them. On the Moon, equipment degrades through abrasion by ultrafine glass particles, thermal cycling across 300 degrees every 29 days, radiation damage to polymers and electronics, electrostatic dust accumulation on every exposed surface, and micrometeorite bombardment that can puncture thin materials or damage delicate components. These processes operate simultaneously, continuously, and cumulatively. No terrestrial testing environment can replicate all of them at once, because no environment on Earth combines hard vacuum, extreme thermal cycling, charged abrasive dust, unshielded radiation, and micrometeorite flux in the same package. This means that reliability predictions for lunar surface equipment are inherently uncertain. Engineers can test components in vacuum chambers. They can test them under thermal cycling, They can expose them to simulated regolith, they can irradiate them. But they cannot do all of these things simultaneously in the exact combination that the lunar surface imposes, and they cannot do it for the durations that a sustained presence requires. The actual failure rates of equipment on the moon will only be known after equipment has operated on the moon for extended periods. And every failure on the moon carries consequences that are categorically different from failures on Earth, because there is no supply chain, no repair depot, no replacement parts warehouse a truck can deliver from. Everything on the moon was brought from Earth at a cost of roughly $10,000 to $50,000 per kilogram of delivered mass, depending on the architecture. A broken seal is not an inconvenience. It is a potential emergency that requires either a spare part that was pre-positioned at enormous expense or an engineering workaround that must be improvised with whatever materials are at hand. Apollo astronauts, despite spending only hours on the surface, came to understand this with visceral clarity. Their post-mission debriefs returned again and again to the dust. It was not a minor annoyance. It was not a cosmetic issue. It was an operational threat that affected every aspect of surface activity. Gene Cernan, the last human to walk on the moon, stated after Apollo 17 that he regarded lunar dust as one of the most significant challenges to future operations. Some Apollo crew members went further, suggesting that dust might be the single biggest obstacle to any sustained human presence on the lunar surface. That assessment was made after 3-day missions in the relatively benign equatorial regions during lunar morning. The south polar environment that Artemis targets is colder, darker, and less understood than anything Apollo encountered, and the dust there is the same relentless, charged, razor-edged material that defeated seals and clogged joints in 1972. 53 years have passed since those warnings were issued. Significant engineering progress has been made. Electrodynamic dust shields, which use oscillating electric fields to repel charged particles from surfaces, have been tested on the International Space Station and shown to remove over 99% of dust from coated materials under vacuum conditions. New suit designs incorporate improved joint seals, dust-resistant fabrics, and modular components that can be replaced if contaminated. Habitat concepts feature suit-lock airlocks designed to keep contaminated suits outside the pressurized volume, preventing the kind of cabin contamination that Apollo crews experienced. Filtration technologies are being developed for the ultrafine particle sizes unique to lunar regolith, but none of these solutions have been validated on the moon. None of them have operated in the actual charged dust environment under real thermal cycling, with real micrometeorite flux for the durations that sustained operations require. They are laboratory successes awaiting field confirmation on the most hostile testing ground in the inner solar system. The gap between terrestrial validation and lunar reality is precisely the gap that has defeated assumptions about the moon before. The moon is not an empty stage waiting for human activity. It is an environment that actively resists human presence through mechanisms that operate at every scale, from the molecular chemistry of dust surface reactions to the ballistic trajectories of micrometeorite ejecta. It corrodes what you bring. It coats what you expose. It grinds what you move. It charges what it touches and makes it cling to what it should not. It is a surface engineered by 4.5 billion years of unshielded bombardment into the most abrasive, adhesive, and penetrating fine material in the explored solar system. And unlike the hazards of vacuum, radiation, and temperature, which can at least theoretically be addressed by building better walls between the astronaut and the environment, the dust cannot be walled out entirely, because the mission requires going outside and interacting with the surface. Every excursion is a contamination event. Every return to the habitat is a potential vector for bringing the enemy inside. This is what separates the moon from merely being a place that lacks protection. The moon is a place that fights back. And it fights with a patience and persistence that no human schedule can outlast, because the processes that generate and mobilize lunar dust never stop. They operated before humans arrived. They operated during Apollo. They will operate during Artemis. They will operate for billions of years after the last human leaves. The dust does not tire. The dust does not diminish. The dust is the surface, and the surface is the mission, and the two cannot be separated. The question then is not whether these hazards can be survived for hours. Apollo answered that. The question is whether they can be survived for months, for years, for the duration of anything that deserves to be called a return. And answering that question requires confronting the full scope of what returning actually means. There is a version of this story that ends with a simple conclusion: the moon is dangerous. Do not go. But that conclusion would be dishonest, and it would miss the actual point entirely. Humans can go to the moon. We proved that in 1969. We proved it 5 more times after that. The question was never whether human beings could physically reach the lunar surface and survive for a few hours. The question, the one that actually matters, the one that the phrase "going back quietly" obscures, is what happens when you try to stay. Apollo was an act of arrival. Every mission was designed around the same fundamental architecture: launch, transit, land. Spend a controlled number of hours on the surface. Collect material. Depart. Return to Earth. The entire system was optimized for brevity. The lunar module carried enough oxygen, water, and power for a maximum surface stay of roughly 75 hours, and most missions used significantly less than that. The command module orbiting above carried enough consumables for the round trip with carefully calculated margins. Nothing was reusable. Nothing was left behind in a functional state for the next crew. Each mission was a self-contained event, a closed loop that began at Kennedy Space Center and ended in the Pacific Ocean. The moon was not a destination, in the sense that a place you intend to occupy is a destination. It was a waypoint, a place you touched and released, like pressing your palm against a hot stove just long enough to prove you could do it. This architecture made Apollo possible precisely because it avoided every long-term problem the moon presents. Radiation exposure over 3 days is well within career dose limits. Thermal cycling across a single lunar morning is manageable with the materials and systems that 1960s engineering could provide. Dust contamination over a few extravehicular activities is an irritant, not a systemic threat. Bone and muscle loss in 1/6 gravity over 72 hours is negligible. The life support math works because the consumables can be carried. The reliability math works because the systems only need to function for days. Apollo succeeded not by solving the moon's hostility, but by minimizing exposure to it. The visits were so short that the environment did not have time to fully manifest its dangers. Every version of returning to the moon that matters, every version that justifies the word return rather than the word visit, involves staying longer. And staying longer does not scale linearly. It scales exponentially in difficulty because the moon's hazards are cumulative, interactive, and compounding. Consider radiation. The dose rates do not reset when you wake up each morning. They accumulate. A 3-day Apollo sprint kept exposure within safe margins precisely because it was 3 days. Extend that to 30 days and the cumulative load enters the range where career dose limits become a real planning constraint. Extend it to a year, and you approach or exceed the thresholds that agencies consider acceptable for an entire career. And that is before a single solar storm adds to the total. The problem is not just the quantity, it is the permanence. Every millisievert received on the lunar surface becomes part of the astronaut's lifetime dose record. It cannot be undone. It does not heal like a wound or reverse like muscle atrophy after returning to gravity. The DNA damage accumulates in cells that may not express the consequences for years or decades. An astronaut who spends 6 months on the lunar surface and returns home healthy may develop radiation-induced cancer 15 years later, and the causal chain traces back to every hour spent on that surface and every cosmic ray absorbed while standing on it. This delayed consequence makes radiation uniquely insidious among the moon's hazards. Dust degrades equipment visibly. Thermal cycling stresses structures on a schedule you can track. But radiation does its worst work silently, invisibly, on a timeline that extends far beyond the mission itself. Shielding is the only countermeasure. and effective shielding demands mass. Aluminum habitat walls help but cannot stop the highest energy galactic cosmic rays, which penetrate several centimeters of metal. The most practical solution remains burying habitats under 2 to 3 meters of regolith, but that requires earth-moving equipment and surface construction capability that must be operational before the crew arrives. Until such protection exists, early missions will accept exposure rates that no occupational health standard on Earth would permit for any worker in any industry. Consider thermal management over extended periods. Those temperature extremes are not merely harsh conditions that a habitat must endure once. They are a recurring mechanical assault on every structure exposed to the full cycle. A habitat's thermal control system must perform two contradictory functions: rejecting heat during the day and retaining it during the night, switching between these modes reliably every 2 weeks for as long as the mission continues. The thermal stress on structural components, seals, joints, and external surfaces is immense. Materials expand and contract, interfaces shift, sealants degrade. Every cycle introduces microscopic damage that accumulates over time. On Earth, buildings are designed for annual thermal cycling across perhaps 50 degrees. On the Moon, the habitat must survive 300-degree cycling every month. Extrapolate that over a year and you have 12 full thermal cycles of extreme amplitude, each one testing every joint and every seal in the structure. No terrestrial building code addresses this. No terrestrial material certification process tests for it. The engineering must be developed, validated, and trusted essentially from scratch. Consider dust over weeks and months rather than hours. Every extravehicular activity brings regolith back toward the habitat. Even with suitlock-airlock designs that keep contaminated suits outside the pressurized volume, some dust transfer is inevitable. Particles cling to tools that are brought inside. They adhere to sample containers. They accumulate on the suitlock mechanism itself, potentially degrading its seals over repeated cycles. Inside the habitat, any dust that enters becomes a permanent contaminant because there is no way to vent it outside without losing atmosphere. Filtration systems must capture particles down to submicron sizes continuously, and the filters themselves must be replaceable because they will eventually saturate. The long-term respiratory risk to crew members depends on the cumulative internal dust concentration over the mission duration, a parameter that has never been measured in an actual lunar habitat, because no such habitat has ever existed. Consider the gravitational effects compounding over time. A crew arriving on the Moon after a 3-day transit in microgravity begins their surface stay already in a slightly deconditioned state. The 1/6 gravity on the surface provides some loading, but, as the evidence suggests, not enough to fully maintain musculoskeletal and cardiovascular health. A crew staying for 30 days will likely experience measurable bone density reduction and muscle function changes. A crew staying for 6 months will face more significant degradation. And then they must return to Earth, re-entering at velocities that impose several times Earth's gravitational force on bodies that have been living in 1/6 gravity for half a year. The physiological challenge of that transition has never been tested, because no one has ever spent 6 months in partial gravity. The data from the International Space Station involves microgravity, which is a different condition. The closest analogue, extended bed rest studies on Earth, suggest that partial unloading produces partial deconditioning, but the exact trajectory under 1/6 gravity over months remains unknown. To understand what this convergence of hazards actually means in practice, it helps to imagine what a 30-day surface mission would look like from the inside, not the version in the press release, not the version in the animated mission concept video with clean suits and sunlit habitats. The version that the engineering constraints and environmental realities we have been walking through would actually produce. Day 1. The crew lands. The descent engine blasts regolith outward at hundreds of meters per second, sandblasting any pre-positioned equipment within a kilometer radius. The crew powers up the habitat, checks the seals, pressurizes the interior, and begins the process of verifying that every life support system survived the transit and landing intact. Outside, The charged dust displaced by the landing has already begun settling onto every external surface, including the solar panels that the habitat depends on for power during the 14-day day. By day 3, the first extravehicular activities begin. The crew exits through the suit lock, walks across the regolith, and begins surface operations. Within minutes, dust coats their suits from the boots upward. It embeds itself in the outer fabric. It clings to visor surfaces, reducing visibility. It works into the joints of the gloves, adding resistance to every finger movement. When they return to the suit lock, the contaminated suits stay outside, but the tools come in. Sample containers come in. Anything that contacted the surface carries particles with it. The habitat's filtration system begins processing these particles, but the finest fraction, the submicron glass shards, challenges even advanced filters. The crew notices a faint metallic smell that was not there before. It is the same smell the Apollo astronauts reported. The smell of reactive lunar dust meeting moisture and oxygen for the first time. By day 7, the routine has been established, but the cumulative effects have begun. The radiation dosimeters show a steady climb. The crew's cumulative exposure is already equivalent to several months of natural background radiation on Earth, compressed into a single week. The thermal radiators on the habitat exterior show the first measurable degradation in performance from dust accumulation, meaning the thermal control system must work slightly harder to reject heat during the long lunar day. The crew exercises daily, but they can feel the difference that 1/6 gravity makes. Movements feel easy, almost playful, but the ease is deceptive. Their cardiovascular systems are slowly deconditioning. Their bones are experiencing reduced loading with every step. The body interprets the lighter gravity as a signal that less structural support is needed and begins quietly dismantling bone density that took years to build. By day 14, the sun sets. For the first time in the mission, the habitat enters lunar night. External temperatures begin dropping, and they do not stop dropping for 2 weeks. The solar panels go dark. Whatever power, storage, or nuclear system the habitat relies on must now sustain life support, heating, lighting, communication, and equipment operation through 336 hours of unbroken darkness. The thermal control system reverses its entire operating mode, shifting from heat rejection to heat retention. The structural materials of the habitat begin their contraction phase as external temperatures plunge past -100 degrees Celsius and keep falling. Seals that expanded during the 2-week day now contract. The crew listens for the sounds of a structure adjusting to thermal stress, sounds that no engineer on Earth has heard from a real lunar habitat, because no real lunar habitat has ever experienced a full night cycle. By day 21, the crew is deep in the lunar night. They have not seen the sun in a week. The external landscape is lit only by earthshine and starlight, assuming the terrain geometry allows even that. The habitat is functioning, but every system is operating under conditions that have never been tested at this duration outside a laboratory. The air filtration system has been running continuously for 3 weeks, processing whatever dust entered during the first 2 weeks of surface operations. The crew's radiation exposure continues to accumulate even during the night, because galactic cosmic rays do not follow the sun's schedule. The dosimeters climb regardless of whether the surface is lit or dark. If a solar particle event occurs during this period, the crew will shelter inside the habitat and hope that the mass of the walls is sufficient. There is no option to evacuate. The ascent vehicle requires preparation time. Earth is 3 days away. A solar storm delivers its dose in hours. By day 30, the sun rises. The habitat survives the thermal transition back to daylight. The seals hold. The power systems resume solar charging. The crew prepares for departure, and they leave the moon having spent 1 month on the surface. 1 month. A single lunar day-night cycle. And every system they brought, every physiological parameter they can measure, every component of the habitat and suits, has been degraded by the cumulative effects of radiation, thermal cycling, dust contamination, and reduced gravity acting simultaneously for 30 continuous days. This is not a nightmare scenario. This is the baseline. This is what 1 month looks like if everything works correctly. If nothing breaks, that was not supposed to break. If no solar storm occurs, if no micrometeorite strikes a critical system, if no seal fails, if no filtration system saturates prematurely. This is the optimistic version, and it is punishing enough that no space agency on Earth has yet built and certified the systems needed to attempt it. Every one of these hazards interacts with every other one. Radiation damage is harder to repair in a body weakened by gravitational deconditioning. Dust exposure is more dangerous to lungs, already stressed by immune suppression from reduced gravity. Thermal cycling degrades the seals that protect against vacuum, and vacuum integrity is the foundation upon which every other survival system rests. A dust-contaminated thermal radiator overheats equipment that was already operating near its thermal margins because of the 14-day day. A power system dependent on solar panels degraded by dust accumulation cannot maintain the life support systems at full capacity during the transition to lunar night. The failures cascade. Each individual problem is severe. The combination is formidable in a way that no single test facility on Earth can replicate, because no terrestrial environment imposes all of these stresses simultaneously. This is why the Artemis program's timeline and structure have evolved so dramatically. But what matters here is not the specific dates or the individual technical setbacks. What matters is the pattern. Every delay in the Artemis program has been caused by a specific physical or engineering problem that proved harder to solve than the original schedule assumed. And those problems involve only the transit vehicle, the rocket and spacecraft that carry the crew to the moon and back. They do not even touch the surface systems. The lander, the suits, the habitats, the power infrastructure, the dust mitigation systems, all of which must function flawlessly once they reach an environment that has never been tested at operational scale, represent an entirely separate layer of engineering challenge that sits on top of the transit challenges already causing delays. The transit problems are difficult, the surface problems are harder, and the surface problems have not yet begun to be tested in the real environment. These delays are not mentioned here as criticism of the program. They are mentioned because the specific failures are revealing. Consider the heat shield. When Orion re-entered Earth's atmosphere in December of 2022, after its uncrewed lunar flyby, the ablative material charred unevenly. Sections that were expected to erode in a smooth, predictable pattern instead lost material in irregular chunks. The char layer fractured and separated in ways the thermal models had not predicted. The crew cabin remained protected, the spacecraft survived. But the discrepancy between predicted and actual erosion meant the models were wrong. And models that are wrong about heat shield behavior at 25,000 miles per hour cannot be trusted with human lives until the discrepancy is understood. That investigation took more than 2 years. It required ground testing, computational analysis, and ultimately a determination that the existing shield was safe enough for crew, but that future shields would need redesign. A heat shield. One of the most fundamental components of any spacecraft returning from beyond low Earth orbit, and it took 2 years to understand why it behaved differently than expected during a single re-entry from lunar distance. Battery packs aboard the European service module also failed vibration testing, requiring replacement and recertification. These are not exotic components. Batteries and heat shields are foundational technology. Yet the specific conditions of lunar-class missions were enough to expose weaknesses that ground testing alone had not revealed. The landing system itself represents an engineering challenge that Apollo's lunar module addressed for a very different mission profile. Artemis surface missions intend to land near the lunar South Pole, a region of extreme terrain with steep crater walls, boulder fields, permanently shadowed areas immediately adjacent to sunlit ridges, and slopes that create hazardous landing conditions. The lighting conditions at the South Pole create a specific and severe hazard for landing. Shadows at the South Pole are not brief patches of shade. They are permanent features of the terrain, some stretching for kilometers, filling entire crater floors with darkness that no sunlight has touched in billions of years. A landing system descending toward this environment must distinguish between a safe flat surface and a boulder field hidden in shadow. Using orbital maps that resolve features down to roughly 1 meter but cannot reveal what lies in the permanently dark zones. The terrain that looks clear from orbit may contain obstacles invisible until the lander is meters above the surface and committed to touchdown. The Starship human landing system being developed by SpaceX for Artemis is an entirely new vehicle architecture, vastly larger than the Apollo lunar module, requiring orbital refueling before it can perform the descent. This refueling process, which involves multiple tanker launches and cryogenic propellant transfer in orbit, has never been demonstrated at the scale required. It is not an incremental improvement on Apollo-era technology. It is a fundamentally new capability that must be developed, tested, and certified before a single crew member descends to the surface. None of this is impossible. All of it is extraordinarily difficult. And the difficulty is not primarily political, financial, or managerial, though those factors contribute. The difficulty is physical. It comes from the moon itself. It comes from the vacuum, the radiation, the thermal cycling, the dust, the gravity, and the unrelenting hostility of an environment that has no interest in accommodating human presence. The engineers working on Artemis are not failing. They are confronting reality. And reality is harder than the comfortable illusion of the moon's familiarity ever suggested. This leads to the realization that sits at the center of this entire story, the one that the title of this episode points toward, but that requires the full weight of evidence to properly understand. The reason returning to the moon is so difficult is not that the moon is far away. It is not. 3 days. A long weekend in transit. The reason is that the moon is close and still this hostile. That combination is what shatters the intuition. Human beings are psychologically prepared for distant things to be dangerous. The deep ocean is dangerous. Antarctica is dangerous. Mars is dangerous. Deep space is dangerous. Distance and danger are linked in the human mind, and when a destination is both far away and hazardous, the reaction is appropriate caution. But the moon breaks this heuristic. The moon is right there. You can see it tonight. You can point at it with your finger. It is closer than some places people fly for vacation. And yet its surface presents an environment so extreme that more than 50 years of engineering advancement have not yet produced the systems needed for a sustained human presence. This is not a failure of technology. It is a revelation about the nature of space. The moon is the nearest major world beyond Earth, the closest substantial body in the solar system, the one destination that should be the easiest, and it is brutal enough to demand the most advanced engineering humanity can produce simply to allow a few people to stand on it for a few weeks. If this is what the nearest destination requires, what does that tell us about the actual difficulty of sustained human presence anywhere else? If the closest world beyond our own atmosphere is this hostile, how should we recalibrate our expectations about Mars, about the asteroid belt, about the moons of Jupiter and Saturn, about every other destination that casual conversation treats as merely a matter of building bigger rockets and waiting long enough? The moon does not answer that question gently. The moon answers it by killing everything it touches, slowly, persistently, through mechanisms that operate at every scale from the molecular to the geological. The moon answers it by showing that even 239,000 miles of distance, even 3 days of travel time, even a destination we have literally walked on before, is enough to expose the total fragility of human biology in the absence of Earth's protection. You do not need to travel to Mars to discover how hostile space is. You do not need to journey to Europa or Titan or the outer reaches of the solar system. You can learn everything you need to know about the relationship between human life and the cosmos by traveling to the single closest world available and trying to stay there for a month. The moon is not too far. That is the uncomfortable truth. The moon is too close for the lesson it teaches to be ignorable. If it were farther away, we could dismiss its hostility as a consequence of distance. We could tell ourselves that nearby destinations must be more manageable and that the extreme dangers only apply to the deep solar system, but the moon will not allow that comfortable story. The moon sits right next to us, practically within arm's reach by cosmic standards, and it is savage. Its surface temperature swings would destroy most industrial equipment within a few cycles. Its radiation environment would measurably increase cancer risk within months. Its dust would degrade respiratory function, mechanical systems, optical surfaces, and thermal management simultaneously, progressively, without pause. Its gravity would allow your bones and muscles to weaken even as you walk and work. Its vacuum would kill you in 90 seconds if your suit integrity failed. And all of this is the easy destination. All of this is the warm-up. All of this is the place we are supposed to practice before attempting something harder. The honest framing of lunar return is not that it is impossible. It is possible. Apollo proved that the moon can be reached. Artemis will prove, eventually, that the moon can be reached again with modern systems. The engineering will advance. The dust mitigation technologies will improve. The radiation shielding will develop. The thermal management systems will become more robust. Habitats will be built. Power systems will be deployed. Humans will walk on the moon again, almost certainly within the next several years. The honest framing is that every one of these achievements will be won against the active resistance of an environment that is fundamentally incompatible with human life, at a cost in money, time, engineering effort, and risk that vastly exceeds what the phrase "going back" implies. Going back to the moon sounds like returning to a place you have been. It sounds like revisiting a familiar location. It sounds manageable, routine, overdue. The reality is that going back means entering the most hostile environment that any human crew has ever been asked to work in for an extended period, at a destination where every survival requirement must be engineered from zero, where every system must function without interruption in conditions that degrade everything they contact, where the margin between survival and catastrophe is measured in the thickness of a suit wall or the reliability of a filtration system, and where the only rescue option involves a 3-day journey home through the void that separates the moon from the only world in the known universe where human beings can survive without machines. The moon does not care that it is close. The moon does not care that we have been there before. The moon does not care about our schedules, our budgets, our political ambitions, or our cultural nostalgia for Apollo. The moon is a world without atmosphere, without magnetic protection, without thermal moderation, without breathable air, without sufficient gravity, and without mercy. It is covered in a material that attacks human lungs and human machinery with equal indifference. It is bombarded by radiation that human tissue cannot withstand for long. It cycles between temperatures that would destroy most materials humans use in everyday life, and it is right next door. That proximity is not a comfort. It is the most important fact in this entire story. The moon is close enough that we can see it, close enough that we can reach it in days, close enough that we can talk to people standing on it in real time, and it is still hostile enough to demand the absolute limit of human engineering capability for even a brief, sustained presence. This is what the moon reveals about the human relationship with space. Not that space is vast and distant, though it is. Not that other worlds are alien and unreachable, though most are. But that even the nearest, most familiar, most seemingly accessible world beyond our own is an environment so fundamentally incompatible with human survival that merely standing on it for a month requires solving problems that half a century of technological progress has not yet fully addressed. This is the harsh truth the title promised. Not that we should never go, not that exploration is pointless, not that the moon is a dead end. The harsh truth is that the moon, humanity's closest neighbour, the one world we mentally categorize as practically next door, is so hostile that going back in any meaningful sense forces us to confront how thin the margin of human survival really is, the moment we step beyond the atmosphere of the only planet that has ever kept us alive. The footprints from Apollo are still there, undisturbed, perfectly preserved in the regolith. No wind has touched them, no rain has eroded them, no microorganism has colonized them. They sit in vacuum, in silence, in alternating extremes of heat and cold, on a surface that charges its own dust and grinds everything it touches. They will remain there for millions of years, long after the civilizations that made them have risen and fallen and risen again, because nothing on the moon ever changes anything. Nothing weathers. Nothing softens. Nothing decays through the gentle processes that Earth uses to reclaim what is left behind. That is not preservation. That is a warning. The moon does not erode those footprints because the moon has no mechanism for gentleness. It has no air to carry sound. It has no water to sustain life. It has no soil in which anything can grow. It is a world frozen in violence, shaped by impacts, blasted by radiation, baked and frozen in endless alternation, and completely indifferent to whether human beings find it beautiful from 239,000 miles away. We will go back. The engineering will get there. The suits will improve. The habitats will be built. The dust will be mitigated, partially, imperfectly, enough to allow crews to work for weeks and eventually months. The radiation will be shielded against with mass and architecture and operational protocols that limit exposure. The thermal cycling will be endured by materials and systems designed specifically for the most extreme environment human engineers have ever been asked to build for. All of this will happen because the species that looked up at the moon and decided to go there is not the kind of species that stops when the problem turns out to be harder than expected. But when we go back, we should go back knowing what we are walking into. Not the moon of cultural memory, not the moon of Apollo photographs and planted flags, not the moon that looks so peaceful and close on a clear night. The real moon, the one that strips away every protection your planet gives you, attacks every system you bring, and does not soften a single one of its hazards because you travelled only 3 days to reach it. The moon that teaches, with absolute clarity, that closeness is not safety, that familiarity is not understanding, and that the nearest world beyond Earth is already hostile enough to expose exactly how fragile human life becomes the moment it leaves home.